we'll talk about these things later. I'm going to begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class. Just ask you to bless our work today. Help us to glorify you what we do and understand a little bit more about linear algebra together, Lord. You know my prayer, Lord Jesus. Amen. Okay, so if we have a vector space, and I'm keeping it real, right? So we have a vector space over R, and if we have a bilinear form B, then if we define Q by B of XX, this is a quadratic form on V, right? So, and then of course if you have a quadratic form, you can define the matrix of a quadratic form, you know, like, so the matrix, and I'll just use a single beta since, you know, the matrix that of Q with respect to beta is one half B of VI Vj plus B of Vj VI. Right? So notice that, notice from our definition, what can you say about our definition then? What can you say about the matrix of Q if this is the definition of it? So notice, like, if this is the ijth component, right, which is what I mean there, right? If you want, I can say, like, the ijth component is equal to this. Maybe that's more helpful. Yeah? So if that's the case, can you tell me this is definitely equal to what? Same thing with J and I reversed, right? In other words, it's a what? Yeah, so let me put some parentheses out here. So, just a second, I'll get it eventually. Oh, you guys an extra parenthesis there. So, yes, Q sub beta transpose is equal to Q beta. That beta doesn't go on the sub Q, it has to go on the brackets, you know? Q sub beta itself doesn't, that would be kind of nonsense in my notation. So it's symmetric. What does that mean? What does that say about this matrix? It's what?
That's the same as Q, the matrix of Q adjoint. Oh wait, no, it's not a linear transformation.
Okay, well, I mean, the matrix is self-adjoint. What's that tell us about the matrix? It can be what? It's orthonormally diagonalizable, right? Orthonormally diagonalizable by the real spectral theorem, right? So just to make some progress here, let's look at the particular case where we have a quadratic form, say from Rn to R, right? In that case, we have Q of x is equal to x transpose times the matrix of Q times x again, right? So this would be, I'm proposing that this is the, matrix of Q with respect to what?
Standard basis?
The standard basis, yeah. So, okay, great. What would happen if we do a coordinate change on Rn? What's that look like? So let's let y equal, let's say, phi beta of x, right? where beta is some possibly non-standard basis. What's the formula in this case? Remember, we do the matrix of the basis inverse times x. That's the formula for coordinate change. Or if you prefer, we could solve for x, right? Solve that for x, what do we get? The, beta times y, right? So to convert from the standard Cartesian coordinates x to the non-standard coordinates y, we can use this formula. And we can just substitute, right? So like q of x, we could rewrite as, I'll just do it here. So x transpose is actually what? It's actually the matrix of beta times y transpose times the matrix with respect to the standard basis q times beta y again. So what happens here? We get sock shoes, right? Y transpose times beta transpose times the matrix of q times beta again times y. We could work out from this matrix Q, like there's a general identity that can be worked out. Let me try to write down. I'll probably regret this, but Q of x, it would be equal to x beta transpose times the matrix of Q with respect to beta times the matrix of x, the coordinate vector of x, like that. Like that's straight up the formula for Q in terms of its matrix. We have to, x is an abstract vector, right? So I can't just multiply by x transpose and x on the left and the right. That would be nonsense. I have to feed it through the coordinate map to convert it to column vectors and row vectors appropriately. But like that's how this goes, right? So generically speaking, if I have a quadratic form and the formula is like this, I can identify whatever's in the middle as the matrix with respect to the, the basis. Like here, if you look at this, this has to be the matrix of Q with respect to beta. Because, this is x beta transpose and this is x beta. So I can see from this that the coordinate change for the quadratic form, at least for columns, right, for the context of Rn, it's like this. Which is quite different, right, than the coordinate change for like a linear transformation. So again, while this is a symmetric matrix defines a quadratic form, right? The coordinate change property for it is quite different than, just a linear transformation from Rn to Rn, for example. Question? Comment? Nothing? Okay. So what does the real spectral theorem say? The real spectral theorem says that if I choose beta to be a, it says that if I choose the eigenbasis, right, beta with eigenvalues for my matrix, let's say Q, then I can write the formula for Q of x instead as, the eigencoordinate for x times the, beta transpose Q beta x beta, right? But I can make this more. I'm missing something here that's kind of important. the real spectral theorem says that we can do better than just choose an eigenbasis. We can do what? We can choose a orthonormal eigenbasis, right? And so in that context, that of course means that this is actually the inverse matrix, right? The transpose of the basis matrix is equal to the inverse matrix. But anyway, the long story short of it is that this gives me, the y coordinate. Well, I guess I'll just call it y transpose. And what's this? It's the diagonal matrix with the eigenvalues down the diagonal, right? And this over here is y again. And when you write that out, we've got lambda 1 times y1 squared plus lambda 2 times y2 squared plus plus lambda n yn squared, right? So the formula for the quadratic form becomes very, very nice if we use the eigencoordinates. Yeah? So I think we've done this before, but I just wanted to kind of circle back and review it again. And this, while I'm doing this over Rn, just to keep things simple, it could equally well be done for an arbitrary real inner product space, right? Because we have the spectral theorem there just the same. It's just the calculations, as you've experienced on the quiz today, could be less pleasant. Sorry, too soon? So let us talk more about bilinear maps. There are so if we have one, so let's suppose we have a bilinear map from V cross V to the reals again, okay? B is symmetric to B is antisymmetric three, B is nondegenerate. Definitely of something. So what are the, how do we define these terms carefully? So symmetric is what it sounds like, right? So we have B of xy equals to B of yx for all x and y in V. That's symmetric. Antisymmetric, same thing, but with a minus. All right, what does it mean for B to be non-degenerate? That's a little bit trickier. What that means is that if B of x comma y is equal to 0 for all y, well, let me make sure I define it exactly as I've defined it in the notes. For all y in V, then what's that imply? X equals to what? What's that? 0. Very good, yeah. So this is non-degenerate. There is a natural proposition that follows from this, right? Like proposition if, M equals to, well, let's say Mij is equal to B of Vi comma Vj, where, B is a bilinear map on V, and the basis is V1 through Vn, then 1, B is symmetric if and only if what? 2. B is antisymmetric if and only if what? 3. 3 is kind of the more interesting one. B is nondegenerate if and only if what? In terms of the matrix of B. So Mij is the matrix, right? But would you, B is symmetric if and only what? M transpose is what? M transpose is equal to M. In other words, the matrix of the bilinear form is symmetric. And it's antisymmetric if and only if the matrix of the bilinear form is antisymmetric. And it's non-degenerate if and only if the matrix is what? Tell you what, let's work out one of these symmetric or antisymmetric before we come back to 3 then. So let's try it out. So B of Vi Vj is equal to B of Vj Vi if it's symmetric, right? Which implies what? Mij equals to Mji, which implies M transpose equals to M, right? Conversely, what if the matrix is symmetric? If we have B of Vi Vj, my bad, if we have Mij equals to B of Vi Vj is equal to Mji, which is equal to B Vj Vi, then remember B of xy is equal to what? The sum over I and j of B of Vi Vj times x upper I, y upper j, where x is equal to the sum of x upper I, v lower I, and y is equal to the sum of y upper j, v lower j. So here I'm dropping back into the last lecture where we found the formulas for the bilinear expansion in terms of the basis. In fact, we defined a notation b sub ij in this context, I think. Maybe I didn't, but you know, left to my devices, I'll start calling this thing bij, right? It's the ijth component of the bilinear form with respect to the beta basis, technically. But anyway, the point is, if that's true on the basis, then you can flippy-flop it, you know, at the basis level, right? And then you can, of course, switch the order of these without any cause for consternation because, you know, that's that. And then you just bring the sum back inside. And perhaps a more orderly way to prove this carefully would be to, you know, just prove that. You could prove a lemma that if it's symmetric on the basis, it's symmetric on the whole space. That's an easy lemma to prove. Prove that if a bilinear form is symmetric on the basis, then it must be that its bilinear extension to the whole space is likewise symmetric. That's what I'm in the midst of proving, essentially. But you know, this is B of yx. So there you go. That's the converse direction. So what I'm trying, the larger thing I'm trying to tell you is if we have information about the matrix, then we can put together the formula for the bilinear form, right, using the coordinates of the vectors involved, and that gives us a formula for the bilinear form in terms of its matrix. And then, of course, we can make whatever manipulations were allowed at the level of the matrix, right? I mean, another way to say this is Bij is equal to Bji. You know, here M is the matrix formed by the ij components of B, if you like that old notation. Anyway, so that proves 1. And the proof of 2 is nearly the same. Now let's return to 3. Can you guys tell me about 3? Say again? Beta is linearly, well, beta is a basis, so that's assumed. I mean, I should say that. My bad. Yes, Brando's laughing at my proof. Ha! Ha! So what do you guys think? Non-degenerate, what's that mean? Like, what do we have? We have, so like the formula for B of x comma y, if you write it in a matrix notation, it's this. It's the coordinate vector of x with respect to the beta basis times m times the coordinate vector of y with respect to the beta basis. That's a formula. There's a transpose here for this. If we want to understand the relation between the matrix and the bilinear form, that's it. So if you have this, so we're saying this is equal to 0, right? For all y in v, right? All y in v, what does this tell us? This tells us for all coordinate vectors of y with respect to basis in where? In Rn, right? If y ranges over the whole of the vector space, then the coordinate vector of y ranges over all possible n column vectors, right? So, Would
that mean that x sub theta transpose times m has to be the 0 matrix?
I don't think that's what we get out of this, no. Let's see here.
Because intermediate.
Let's see here. How to recast it. So, okay, sorry, let me, this implies that x equals to 0, right? So we have whoa. All right, let's see here. All right, so this implies, I think, one of you think just said this a second ago, and I should have listened to you. So you said, well, this means that x transpose beta times m is equal to 0, right? But that is equivalent. See, like, I don't know, I have to look at it. I don't think about row vectors personally. I think about column vectors, right? So this is useless to me. But if I take the transpose of this equation, it all of a sudden has meaning for me as a, you know, a columnist. My in-group preference is columns. Let's see here. So if I take the transpose of that matrix equation, sock shoes gives me that's m transpose x, right? But so this right here implies x equals to 0. What does that mean? what you were saying, Sam, that says that the kernel or the null space of the transpose of M is the zero space, right? But this is a square matrix, which tells me that the determinant of M is not equal to 0. Or if you like, getting to the point eventually, the determinant of the matrix is not equal to 0. Equivalently, we could say that the matrix is invertible. So non-degeneracy of the bilinear form implies invertibility of its matrix, and vice versa. Sorry, I took my sweet time getting to that, but it's just taking it apart piece by piece. You know, if this is true for all y, then we can use the standard basis to select the component after the component after the component after the component. We have every component 0, which gets us to this equation. We transpose that, it gets us to this equation. This equation equal to 0 implies only the 0 solution. The only matrix equation that only has the 0 solution is an invertible matrix. Going back to 221 stuff. All right? So with all that, we now can define geometry. What is a geometry? Here it is. Definition: V, a real vector space if G, a mapping from V cross V to the reals, is symmetric, bilinear. Probably puts bilinear first, really. A symmetric bilinear non-degenerate. You can put these in any order you like, okay? I probably should say bilinear symmetric non-degenerate form on V. Then we say G is a metric. The pair V comma G is known as a geometry. All right. In this context, if you have L is a linear transformation on V, such that G of Lx, Ly is equal to G of xy, then L is a G orthonormal, or G orthogonal rather, mapping. Or if you like, you could call it a linear isometry. It's a linear isometry of the geometry. That kind of rhymes. It's a linear isometry of the geometry. There we go. But yeah, so this is the definition of geometry. Inner product is a special case of this. So an inner product is what? It is a symmetric, bilinear, actually positive definite form. So like the inner product has this property, right? XX greater than or equal to 0. And the inner product of x and x is equal to 0 if and only if x equal to 0, right? This business right here. Next time, we'll look at this some more, and we'll see that that means that the matrix of the inner product, all right, which some of you discovered, it's called the Gramian matrix, right? It's necessarily invertible. a positive definite matrix, as they're called, are invertible. But not every invertible matrix is positive definite. So the idea of a metric is more general than the idea of an inner product. In fact, I already gave you an example of a metric early on. Like my example 2, when we were starting to introduce inner product spaces, was actually an example of a metric which wasn't an inner product. Because we had like 0 from the thing with itself, but it wasn't 0. Anyway, more on that later, but I think that's it for today. So, sorry about the quiz. I was not trying to make it like impossible. It's all, you know whose fault it is, but anyway.